Hello everyone, let's discuss 3 problems from yesterday's Codeforces round. Starting with division 1a, you can read it now or listen to my explanation. In my explanation, you are given an array of length n. You can apply a single operation to it. The operation of such type: replace a segment of values with some single value. Your goal is to increase the max of the array by exactly 1. You need to output if it's possible or not. So the max is the minimal excluded. It's the smallest natural number which is not present in the array. Let's say that max is equal to m, and we want to make it m plus 1, which means that m initially wasn't in the array, but after we'll apply the operation, m must be within the array. It means that the value which we'll be setting on some segment is m. Now we just have to choose a segment where to set all the values to m. First of all, let's consider 2 cases: if the value m plus 1 was in the array, or if it wasn't in the array. If it was in the array, then obviously all the values m plus 1 must be within the segment that we choose to set the value m, because the value m plus 1 must not exist in the array after the operation. Now the max will be equal to m plus 1 if all the values from 0 to m minus 1 inclusively appear here exactly once in those 2 suffix and prefix, which means that we want to maximize those suffix and prefix, meaning that we'll choose the smallest possible segment that just covers all the occurrences of m plus 1, because this way the maximum possible prefix and the maximum possible suffix will be untouched, and so we have the bigger chance to cover all the values from 0 to m minus 1 inclusively. So we just check that all those values appear at least once in those prefix and suffix, and if it's true we output yes, otherwise we output no. Now let's look at the second case when m plus 1 does not occur in the array, so we don't know which segment we must choose, but we still have to choose at least one element for this operation. But as we again want to maximize the size of this prefix and this suffix, we can only consider operations which cover only one element, because this will enlarge either the prefix or the suffix or both, meaning that it will have a greater chance to cover all the values from 0 to m minus 1 inclusively. So we need to just find an element in our array such that all other elements contain the occurrences of all the values from 0 to m minus 1 inclusively, and set it to m. We know that all those values do occur in our array, so if some value occurs twice, we can just choose one of those occurrences. Alternatively, we can just choose any value which is larger than m. If such value exists, then all the other elements cover the values from 0 to m minus 1 on their own. So the only case that we didn't cover is if all the elements are different and none of them are greater than m. So it means that our array is just permutation of values from 0 to n minus 1. But in this case, the max is already n, and we can't make it larger than n if the length of the array is n. So in this case, we should output no. Let's look at the implementation. Here I read the array. For all the values up to n plus 2, I remember if they occurred in the array. In this vector was. Why the size of was is n plus 2 is because I want to include all the possible values of m plus 1. Because later I will check if the value m plus 1 occurs in the array. And as max is at most n, then max plus 1 is at most n plus 1. So up to n plus 1 inclusively, I create this was, I fill it, then I find the minimal excluded, I call it m. Then I check if m plus 1 does not occur, then I reset the was, and I go through the array once more. Now I just want to find an element which is larger than m, or an element which occurs twice. In this case, I set the variable good to true, and in the end, if good is true, I'll put yes, otherwise no. And the other case, if m plus 1 does occur in the array, then I just reset the was, and I check that if I go from the start until I meet a value m plus 1, so the largest prefix which does not contain m plus 1, and if I go through the largest suffix which does not contain m plus 1, will those elements be enough to cover all the values from 0 to m minus 1 inclusively? I check it here, and if it's enough to cover all those m values, then I'll put yes, otherwise I'll put no. That's it. Now let's discuss B. You can read it now or listen to my explanation. In my explanation, we had a rectangle size h by w, and we made cuts either vertical or horizontal, such that the two new rectangles also have integer sides. Then we took one of the rectangles and put it aside and continued to cut the other rectangle. At some point we stopped and also put aside the rectangle that we had at the moment. Now you have those n rectangles and you didn't rotate them, but you don't know the order in which they were put aside. You need to recover all the possible sizes of the original rectangle. Let's see how we got those rectangles. Suppose the first cut was horizontal. And we did some horizontal cuts. And let's say that we've put aside those rectangles, but then we continue to work with the top rectangle. And then we start making vertical cuts. So we did some vertical cuts, and then we continued to work with the leftmost rectangle. Then we started to do horizontal cuts again. If we are sure that the first cut was horizontal, as I said, then we can instantly find this side of the initial rectangle. It is equal to the maximal horizontal side of all the rectangles that we have. And we know that all the rectangles with such horizontal side were made on the first stage of the process. And then all those rectangles will have smaller horizontal size. So now we can recursively solve the problem for just those rectangles which don't have the maximal horizontal size, knowing that now the first cut was vertical. So on this set of rectangles, we'll just set the answer vertical side to the maximum vertical side of any rectangle we have. And then all those rectangles that have such side, we'll put in one group. And all the other rectangles will just recursively call our function again to find the sides of rectangle that they form, but now knowing that the first cut was again horizontal. Of course, when we return from the recursion, we need to check that the size of the rectangle that the recursion gave us fits the side of the bigger rectangle that we've previously determined. If it does not fit, then there is no answer. But if it does fit, then there's only one answer, assuming that we know which type of cut was the first. So now when we have this recursive function, we can just try to call it assuming that the first cut was vertical and assuming that the first cut was horizontal. In each case, we'll get either no possible answers or one possible answer. Then we just unite the results that we have and output all the possible answers that we get. Let's look at the implementation. So this is the recursive function. It actually accepts two references to the sets of rectangles. The rectangles in the first and in the second multiset will be the same rectangles, but in the first multiset they will be sorted by the first side, and in the second multiset they will be inverted. The sides will be swapped, and so they will be sorted by the second side. And the function solve returns the answer for such set of rectangles, assuming that the first cut the second side, and it will return -1, -1 if the answer does not exist. The first thing that we do is take the maximal first side among all the rectangles and take it as a first side of the answer rectangle. Then we sum up all the lengths of the second side through all rectangles which have such first side. So while there are still rectangles and the last rectangle in the set sorted by the first side has such first side, then we pull it from the set, add its second side to the sum, erase it from the first set, and also erase it from the second set, having swapped the two sides. Now, if there are still rectangles left, we want to recursively call our function, but now having SA and SB swapped, this will effectively rotate every rectangle that we still have, swapping their sides. Then we also swap the sides of the resulting rectangle that the recursion returned, and we check if it's -1, -1, or the side of the rectangle does not match the side that we found, then we return -1, -1. Otherwise, we just add its second side to the sum and return the pair side sum. Here in the main function, we read the rectangles, and set of pairs ends will be all the possible answers, all the possible initial sides of the rectangle. We create SA, SB, we put rectangles into SA normally, and inverted rectangles into SB. Then we call for our function, and we check if the result is not -1, -1. Then we add it into the set of possible answers, and then we create those sets anew, and we call for our function, but now having SB and SA swapped, so now we assume that the first cut divided the first side. And swapping SA and SB will effectively rotate every rectangle, so we also have to rotate the resulting rectangle. And then we again check if it's not -1, -1, we add it to the set of possible answers, and then we output the possible answers. That's it. Now let's discuss problem C. You can read it now and listen to my explanation. In my words, you have a tree of n vertices. From a vertex, you can jump into any vertex which is no more than 2 edges apart from it. So you can jump into a neighboring vertex or into a neighbor of your neighbor. You need to start in some vertex V and jump through every vertex of the tree exactly once and return to the same vertex V. You need to output if it's possible or not for a given tree, and if it's possible, you need to output the order in which you jump. Suppose we have hanged the tree by some vertex. Let's also suppose that we start from this vertex. Let's suppose that starting from this vertex, the first sun which we'll visit is this, the second is this, the third is this, and the fourth is this, without loss of generality. When I have arrived into this sun, I don't know where I arrived from. It may have been from this vertex or from some other. But I know that the only way for me to get to the next sun is through a direct jump, because this vertex is already visited before. Let's draw jumps in red. Then from this vertex, I can repeat the same reasoning for this pair of neighbors. The only way to get from here to there is through a direct jump, because I know that this vertex is already visited, so I can't go there, and this vertex must be visited later, so I had to do such jump, and I also had to do such jump. But this means that those two suns were leaves, because if they had some children, then when I arrived here, I had to go somewhere here, but I cannot return from this subtree, because the only way I can escape this subtree is going again to this vertex, but it's already visited, or going here, but it's also already visited. So all the suns of the root, except for at most 2, must be leaves. Now suppose that this sun of the root is a leaf, then it's very easy. You can just go directly there. But let's suppose it's not a leaf, so it has some children. If we go directly into this sun, we have to go there after, so we don't have a chance to visit those vertices, which means that we didn't go directly into the sun, and we went to some sun of this sun. Let's say the first sun which we went for is this, without loss of generality. let's add another sun to this vertex. Let's again say that the next sun which will be visited is this, the next one will be this, and the next one will be this. We can apply the same reasoning to prove that we'll have to execute such jump, and then such jump, and then such jump. But now we can also repeat the same reasoning to prove that all those vertices must be leaves. So not just all but two vertices, but all but one vertices. All but one sun of this sun of the root must be leaves. Then again, we can say that if this vertex is a leaf itself, we can just go from it straight to the sun of the root. But if it's not a leaf, we just continue the same picture. Let's say that again those suns will be visited in this order. It means that when we were here, we had to jump directly into our grandfather. We can potentially visit the subtree of this vertex if we jump like this, but we can't visit the subtrees of all those because we'll have to execute such jumps. So all those suns must be leaves again. So again, this vertex must have at most one non-leaf sun. If it's also a leaf, then again we can do this, but if it's not a leaf, we just continue the same logic. We have to jump here first, then here, then here. Those must be leaves. But then if it's a leaf, we do this. If it's not a leaf, we continue. And so on. At some point, we have to stop. So at some point, we have to have all suns be leaves, like this. And there will be a similar image here. In general case, if it's not a leaf, we have to jump from here. We have to execute such jumps, and those must be leaves, but this can be not a leaf. So in general, the tree must look like this, and the path also must look like this. We'll always have only one possibility to within the order in which we traverse those leaves. But we've actually proven that the tree that can be traversed looks like this. It's some path with some leaves attached to it. And the path will go somewhat like this. To simplify the code a little bit, I find this vertex of the tree, which is a vertex of a tree which has only one non-leaf sun, or zero non-leaf suns. If the tree looks like this, I also accept such vertex as the starting point. So I call this vertex a root, and I hang the tree by this vertex. So then I don't have to deal with that case, because only one of the suns will be not a leaf. If such vertex doesn't exist, then I state that the tree is impossible to traverse. And in the code, I will just run DFS. So I will use a DFS to simulate this process. I'll call the main sun of the vertex the one which is not a leaf. It may not exist, of course, but there almost must be only one main sun. There cannot be two, otherwise I just output no instantly. And the process will have two modes, and it will switch between two modes. First mode is when you want to output your vertex, then traverse your main sun, outputting all the vertices of its subtree, and then output all the suns which are leaves. And the second mode is when you want, on the contrary, first output all the leaves, then traverse and output the subtree of your main sun, and only then output your vertex. And that's basically it. Let's look at the implementation. Okay, so G is the tree, ends, is where I push back the answer, the vertices in the desired order. When I call for this DFS with mode showing the current mode of the process and P showing the parent of the vertex V and -1 if the parent does not exist. First thing I do is I find the main sun, which is just some neighbor of V which is not a parent and which has a size larger than 1. If I see such sun, but I already have a main sun, then I instantly output no because I can have two main suns and exit from the program altogether. Otherwise, I just set main sun to this vertex. Then if mode is true, I first add my vertex to the answer, then I traverse the main sun, and then I add all the leaves. And otherwise, I add all the leaves, then traverse the main sun, and then add my vertex. By the way, I forgot to mention that I don't want the root to be a leaf, because this will be a separate case. So when I'm searching for this vertex which has exactly one non-leaf neighbor, I don't want itself to be a leaf. So n is equal to 2 is a separate case, because in this case all of the vertices are leaves. So in this case I just output yes 1 2. Otherwise I read the graph and I search for this root vertex. So if it's a leaf I skip it, but otherwise I see how many non-leaf neighbors it has. If it has no more than one non-leaf neighbor, then I call the root and I call for DFS from this vertex. In the end, if I didn't, of course, end the program with exit 0, I output yes and I output the answer. That's it for today. Thank you for watching. I remind you that I give private lessons on competitive programming. If you're interested, contact me on Telegram. Goodbye.